Hello students, welcome back. Today we have another session on distributed generation and smart grids. In the last session we had seen various distributed generation and how they can be integrated with the grids, what are the advantages, etc. So today we will see what is a microgrid, what is the concept of a microgrid, and a typical microgrid configuration. So what is a microgrid? So a microgrid is a cluster of loads and micro sources operating as a single controllable system that provides power to its local area. So what does it mean? So a microgrid is a cluster of consumers basically. They have their own distributed generators, their own storage devices, their own loads and their own controlling devices so that they can independently operate depending or not depending on the grid. Normally operates connected to and synchronous with the traditional centralized grid. Normal microgrids, they are normally connected and they work in synchronous. That is very important. The microgrid should be synchronized with the grid. What do you mean by synchronization? You had already studied various conditions for synchronization. Because when we are working with AC, these two ACs should be connected, means they should be synchronized. So what are the conditions for synchronization? You had already studied conditions for synchronization. The first one is both the voltages should be the same. Second is the frequencies should be the same. Thirdly, the phase sequence should be the same. And fourth, the phase angle should be the same. And now we are going to encounter a fifth condition for synchronization. The quality of power, the power quality should be the same. These things we will address a bit later. And the grid and the microgrid, they should be connected, and the point at which they are connected, we call it point of common coupling or PCC. Distributed generators and load in the neighborhood can form microgrids which can work parallel to grid or operate in islanded mode providing UPS services. So if there is a microgrid, it can be connected with the grid or it can work independently. When it is working independently, it is something like providing uninterruptible power services, and we call it islanded mode. So a microgrid is a cluster of loads and micro sources operating as a single controllable system. It can be connected to the grid or it can be disconnected from the grid, and when it is disconnected we call it in the islanding mode. There are other modes, we will come to it later. And this microgrid concept, this is a complete solution for rural electrification. If you want to provide electricity to people living in deep forests or deep inside the deserts, then the only alternative is to have a microgrid. It is not feasible to take overhead lines through long distances just to cater for maybe 20 families living in a forest or 10 families living in a deep inside a desert. So microgrid is a complete solution for rural electrification. This is a picture of a community microgrid. So a community microgrid means a group of consumers come together with their energy resources, storage devices, load, and control station, small control units, so that they can independently provide the energy needs for themselves. So if you see this picture, you can see there are rooftop PV solars which generate energy from sun, micro turbines. So in case of solars are not working, for example in the night the solar may not be working, so they have micro turbines. They have energy storage devices, large huge batteries. They have distributed generators, home energy systems, plug-in hybrid electric vehicles. So there are a lot of electrical vehicles which can be plugged in. Ground PV solar array. So rooftop solar PV solar is there, as well as ground PV solar array is also there. Then they have utility scale energy storage, and also they are connected to the grid. So this is a general picture of a community microgrid. So managing such a community microgrid is not very simple. So we will see what are the different controllers and control actions essential. This is the picture of a conceptual microgrid. Basically it can be divided into three. The first is the distributed energy resources. The second is advanced power electronic interface modules, and third is the load and the utility grid connections. So coming to the distributed energy resources, it can be fuel cells, solar panels, micro turbines, wind turbines, energy storage devices, or even generators. And we need a lot of advanced power electronic interface modules for power conversion, inversion, power conditioning, protection, interfacing the output, controlling the load, then ancillary services, monitoring and control. It's a lot of electronic interfaces will be there. Okay, so sometimes you will be producing DC, so this DC has to be stepped up, then you have to invert it to AC, so you need inverters, you need converters, you need buck and boost converters. So these are all advanced power electronic interface modules. Then lastly, the local loads. So any microgrid has to meet the local load, and then it has to be connected with the utility grid at the point of common coupling, PCC. Why we should go for microgrids? Why we should go for microgrid? When it demands a reliable source of power for your critical infrastructure. So when you have a critical infrastructure where a power disruption cannot be allowed, then you should have a uninterruptible power supply system with you, or a microgrid. This microgrid may be connected with the grid or not. It should ensure uninterruptible power all the time, 24/7. Resilience is the ability of a system to maintain its functionality and behavior after a disturbance. So if there is a disturbance and there is a power outage, so the functionality to maintain is called the resilience. So the ability of the system to maintain its functionality. So when there is a power outage, there is let us say there is a flood and the electric grid fails. So there is a power outage, but the microgrid can still keep working. And that is the ability of a system to maintain its functionality after a disturbance. Green power Once again, the dependability of fossil fuels we are reducing by using renewable energy sources and connecting all these renewable energy sources with the microgrid. It complements my main grid, especially during peak demands. So the main problem with our electric grid is it will be loaded at certain times and it will not be loaded at certain times. For example, during the evening from 7 to 9 or 7 to 10, the load will be maximum. At that time, the generators might fail to supply the load. So a microgrid, if they have excess power, can complement the main grid, or the grid can supply it to the grid. Microgrid can supply it to the main grid. Enhances social well-being. Once again, we come to the rural electrification. People living in faraway places, people living in deep deserts, deep in the forest, their life can be made better by providing electricity, by providing communication. So rural electrification to areas where no electric grid or reliable power. During disasters when critical facilities fail to operate. So this is very important. When there is a disaster and the main grid fails, microgrid will be able to support critical facilities. This is a typical microgrid configuration. So you can see here 3 different types of DGs. The first one is a series of solar panels, and second one you can see a windmill or wind turbine, and thirdly you can see a energy storage system. So there is 2 types of generation and 1 storage here. The output of solar is DC, and this DC has to be converted to AC. So you need an inverter there, and then it is connected to the common AC bus. Similarly, the output of the windmill, it may be AC or DC, depending on it, the condition of it has to also to be converted into AC and connected to the common bus. And battery output is DC. The battery may be charging or it may be discharging. So you need a bidirectional converter over there. So when battery is discharging, the DC has to be converted to AC, and it is again connected to the common bus. On the other side, the loads can be linear loads, non-linear loads, or sometimes the load may be even unbalanced. All these loads are connected to the common AC bus, and this common AC bus is connected to the main grid at a point which is called the point of common coupling, or PCC, through a static transfer switch. So by opening STS, the static transfer switch, you can connect or disconnect the microgrid. This is another configuration of a microgrid. Here you can see 3 feeders: feeder A, feeder B, and feeder C. In feeder A, first you will see a CB1. CB1 is a circuit breaker. Similarly, feeder B, you will see another circuit breaker, CB2. And feeder C also you will see a circuit breaker, CB3. So using this circuit breaker, that particular feeder can be connected or disconnected. A dark thick line is the microgrid bus, which is mentioned here, 415 volt microgrid bus. Now in the feeder A, you will see a CHP source, a non-CHP source, and a storage device. So there are 2 sources, and there is 1 storage device, and each one of them you can see a MC, which is a micro source controller. All these three are in general called micro sources. It may be a CHP source, it may be a non-CHP source, or it can be a storage device, and each one of them has a micro source controller. Feeder B does not have any sources or storage devices. It has only loads. Once again, going back to feeder A, you can see two sectionalizing circuit breakers or SCB. These circuit breakers are used for the purpose of maintenance of particular section. You can open the SCB so that that part will be disconnected and do the maintenance services there. Coming to feeder C, you can see there is one CHP source, one non-CHP source, and a storage device. So it is exactly the same like feeder A. It has loads and it has sectionalizing circuit breakers also. So all these three feeders are connected to a common bus, which is called the microgrid bus, and you can see a controller CC, which is very important, which is called the central controller, which is responsible to control the entire microgrid. We will see central controller in detail later. The microgrid bus is connected to the main bus, and you can see another circuit breaker CB4 between the microgrid and the main grid. So by opening CB4, we can disconnect the microgrid from the main grid. You can also see a 6 kV 415 volt distribution transformer in the main grid. So the microgrid side is 450. So that for the transformer input is coming from the nearest substation. So from the substation, the voltage or the transmission line is a 6 kV transmission line. It comes to the transformer. The voltage is stepped down to 415 volt, and it is synchronized with the microgrid. So in general, a microgrid configuration consists of a group of radial feeders, micro sources like CHP or non-CHP, point of common coupling, a lot of power electronic interfacing devices, storage devices, critical and non-critical loads. Now coming to the microgrid configuration, the operation and control of microgrids is controlled and coordinated by two controllers. One is called the micro source controllers and the central controller, CC. So we will see today micro source controller, MC. The function of MC is to control the voltage profile at load end. So the voltage at the load end should precisely be constant, and power flow of the micro source independently. So that is the main task of the micro source controller. Remember, every distributed generating unit is having its own micro source controller. Ensures each micro source supplies its share in the standalone mode. So when the microgrid goes into a standalone mode means it is disconnected from the grid. It is also called islanding mode. So each micro source has to supply certain amount of the generating share, or it has to meet the certain amount of the load. So micro source controller should ensure that that particular micro source supplies its share. And who will decide its share? It is decided by the central controller, CC. participates in demand side management. What is demand side management? We will see a bit later. Load tracking management and economic generation scheduling by controlling the storage devices. All these things we will come at a later point of time. Secondly, coming to the central controller, or it is also called the microgrid central controller. Its role is overall control. So it has to give instruction to each and every MC or micro source controllers. Maintaining power quality. Provide power dispatch and voltage set points for all micro source controllers. So whenever the microgrid goes into an islanding mode, then the load dispatching activity has to be taken care by the central controller. The central controller will decide what is the load shared by each and every micro source, and that is called the power dispatch, and it will also give the voltage set points to all the micro source controllers, and it will coordinate among the micro source controller to meet the load. The load and the generation should be equal at all points of time. It consists of two modules, energy management module and protection control modules. We will see these modules later in detail. The two functional modules in a central controller are the energy management module. So it provides the set points for frequency, voltage, active and reactive power output to each micro source controller. So that it is the duty of the EMM to provide the set points for voltage, frequency, active and reactive power output. This information has to be supplied to the MC, micro source controller, by the EMM. The protection coordination takes care of the protection. So protection coordination to faults in grid, microgrid, and loss of grid. Loss of grid means sometimes the grid is disconnected. Disconnects grid in case of loss of grid. If there is a loss of grid, immediately the grid has to be disconnected. If you don't disconnect the grid, then the power will start flowing outside. So whenever there is a LOG, loss of grid, the grid has to be disconnected. And who will take care of it? The PCM module, which is within the central controller, will take care of it. Disconnects feeders to stabilize. You should remember that in any power system, the total generation should be equal to the total load at all points of time. So whenever there is a difference, for example, the power generation is less and the load is more, immediately you have to cut off some of the loads. So this means you have to disconnect some of the feeders. So this activity is also coordinated by the PCM. Then once the grid is active, you have to resynchronize the microgrid to the utility grid and connect the microgrid back to the grid. So these are the activities carried out by the central controller in a microgrid. So with this, we wind up for today. Thank you for patiently listening to this session. We will see again tomorrow. Thank you.